In this video, we're going to look at the first major rule of probability, and we're going to look at a few rules of probability. But this is a big one. This is called the general addition rule. It doesn't have a great name, but it is a very important rule. The general addition rule will apply when you are looking at the probability, looking for the probability of event A or event B. In mathematics, it's important to know that by definition, or means one or the other or both. When we use the general addition rule to find the probability of A or B, we take the probability of A, add it to the probability of B, and then subtract the probability of A and B. I would think that as a student, hearing me say that or means one or the other or both, and then saying that we're subtracting off the both, to me that would be very confusing if it was the first time I heard that. But let me explain it this way. When we talk about or, we usually call it a union. So I always think about two people moving into the same apartment. Right? They're coming together, they're forming a union, which means that they're taking all their stuff and putting it in one apartment. Well, whatever they have that's overlapped, it means that they have two of them. So if person A is coming in with a bunch of stuff and happens to have a toaster, and then person B comes in with a bunch of stuff and also has a toaster, then that toaster is getting counted twice, because it's with both person A and person B. But we don't want to count that toaster twice, so we have to subtract off whatever both people have in common, right? We want to sell one of those toasters. That's what this probability rule is doing. All right, let's look at an example. So we have a contingency table. Remember that we studied these in Chapter 3. This one says 1,000 adults were asked whether they favored a law that would provide support for higher education. In addition, each person was classified as likely to vote or not likely to vote based on whether they voted in the last election. What is the probability that a randomly selected adult is likely to vote or favors the law? So we are looking for the probability that they will vote or favor the law, which by the formula means we're looking for the probability that they are likely to vote plus the probability that they will favor the law minus the probability that they will vote and favor the law. So let's look at each of those three probabilities separately. So the probability that one of these, a randomly selected adult, will be likely to vote. So I'm looking at this entire likely to vote row. And if we find the total here, 372 plus 262 plus 87, will give us 721. And remember, we have a total of 1,000 adults. So the probability that a randomly selected adult will vote is 721 out of 1,000. When I want to find the probability that they favor the law, then I'm going to look at the column for favoring the law. And again, I want to total up the 372 and the 451. So 372 and 451 is going to give me 523. So that means that the probability that an adult will favor the law is 523 out of 1,000. Well, now notice that these 372 people, they got counted twice. They got counted in this 721 total as well as the 523 total. We don't want anybody to be counted twice, so we need to subtract off that intersection. It's called an intersection. So we're going to subtract off the probability that somebody is both going to vote and favor the law. So we're going to subtract off this 372 out of 1,000. And that will give us 872 out of 1,000, or 0.872. By the way, notice that I am not trying to reduce my fractions in any way. I'm using my fractions from the table to show my work and then writing my final answer as a decimal. Okay, so a good place to look at OR problems, union problems, is to look at a Venn diagram. So in this case, we have a survey asks students if they were currently in a relationship and if they were involved in sports. 33% of students surveyed said that they were in a relationship and 25% were involved in sports. And 11% answered yes to both questions. So before I get to the probability questions, let's fill in the Venn diagram. So with this Venn diagram, we're going to have two circles. One circle is going to represent the relationships, the students who are in relationships, and the other circle is going to represent the probability that students are in sports. This entire first circle is going to equal the 33%, and I'm going to write it as a probability, so I'm going to write it as 0.33. And then the entire sports circle is going to have to add up to 0.25. We put the probability that people say yes to both, we put that in the middle of the circles. So the 11% that answered both to these questions, we're going to put that number here. And then what we want to do is we want to calculate the value that goes here. That value will be the students that are in a relationship but not in sports. And the value over here will be the students that are in sports but not in a relationship. The biggest mistake that I see students make is they automatically put the 0.33 inside the circle and the 0.25 inside the circle. You shouldn't do that. That 33% for students who are in a relationship, that doesn't mean that they are only in a relationship. It just means that in the relationship data column, they said yes. So when it says, so we got to actually fill in these values. So let's fill in this value. So we know that the entire circle has to equal 0.33. So if we take 0.33 minus the 0.11, we'll get 0.22. And again, this entire circle here should total 0.33. And then looking at the next circle, if I take 0.25 minus 0.11, I'll get 0.14, making it so that this entire circle adds to 0.25. So now it says, what percent of students are involved in sports but not in a relationship? So we're looking at the probability that they are in sports but not a relationship. So we found that by taking the 0.25 and subtracting off the intersection, and we can see that in our diagram we got 0.14. What percent of students are in a relationship but not in sports? Again, we can see it in our diagram, but we took this 0.33 and subtracted off the intersection, giving us 0.22. Okay, now the last question. What percent of students are in a relationship or involved in sports? There's two ways you can go about doing this. We can use the formula, or we can use our diagram. So using the formula, if we're looking at the probability that they're in a relationship or sports, This is going to be the probability that they're in a relationship plus the probability that they're in sports minus the overlap, the probability that they're in a relationship and sports. So we don't want to count those people twice. And we can get all of these values out of the paragraph. We know that the total probability that they are in a relationship is 0.33. The probability that they're in sports is 0.25. And the intersection is 0.11, giving us 0.47. So we can do it that way, or we can use the diagram. So this is just a second method, and it seems just like some people like one way and other people like the other way. So I'll let you choose. Just make sure that if this is an exam question, that you show your work. So if we're using our diagram, remember that or means one or the other or both, meaning only one or only the other or both. So we could add the probability of a relationship or sports. If we didn't want to use the formula and want to use the diagram, this would be the probability of only a relationship plus the probability of only sports plus the probability of a relationship and sports. So notice I'm adding the intersection, and that's because I took it out of the only relationship and only sports. So now I'm not adding it at all. So I got 0.22 plus 0.14 plus 0.11, and we will get the same answer, 0.47. I highly suggest you choose one of these ways and then stick to it for all of the problems. The formula is kind of the easier way to go, but it's really up to you. So, the definition of mutually exclusive. So we want to talk about the general addition rule under this specific scenario. So I first want to talk about what it means for two events to be mutually exclusive. Another word for mutually exclusive is disjoint. So mutually exclusive or disjoint events mean that they have no possible outcomes that they share, no possible outcomes. So for example, if we're rolling a die, if we had one event that was rolling a 3 and the other event that was rolling an even number, well, those two events don't have anything in common, and so they would be considered mutually exclusive. Or say we're choosing M&Ms. There are no M&Ms that have more than one color. So picking a blue M&M and picking a green M&M would be mutually exclusive events, since there are no M&Ms that are both blue and green. An opposite, so a scenario that's not mutually exclusive, would be if I'm in a car dealership and I want to test drive a car, and event A is picking a blue car and event B is picking a car with all-wheel drive. Well, there are plenty of blue cars with all-wheel drive. So those two events would share outcomes, meaning they're not mutually exclusive. Basically, mutually exclusive events would mean that if you had a Venn diagram, there'd be nothing in the middle. The circles wouldn't intersect. They'd be completely separated. So the general addition rule for disjoint events, specifically for mutually exclusive events, means that you don't have to subtract off the intersection. Why? Because there is no intersection, right? The probability of A and B for mutually exclusive events is 0. So that part is left off of the formula. So If you looking at this example, it says in a recent year of the Olympic Games, a total of 11,544 athletes participated. Of these, 554 represented the United States, 314 represented Canada, and 125 represented Mexico. What is the probability that an Olympic athlete chosen at random represents the US or Canada? Well, it's not possible for an athlete to represent more than one country, which means that the probability that an athlete would represent the US and Canada equals 0. So when I'm looking for the probability that an athlete will represent the US or Canada, I did not spell Canada right. Then this would be the probability that the athlete would represent the US plus the probability that they would represent Canada. And I wouldn't need to subtract off that 0. So this would be 554 out of the 11,544 plus the 314 out of 11,544, giving me 868 out of 11,544, which as a decimal is 0.075.